Very good morning, friends. Today's subject of discussion is chemistry of peptides. Here, we are going to deal with the synthetic strategies for peptides. Why peptide synthesis? What's the need? Yes, unless and until there is a need, there is a demand, we never attempt towards that. Yes, when we are useful, then only people come to us. When something is useful, we try to synthesize them as chemists. There are enormous utilization or utility of these peptides. That's why we synthesize them and hence we call it as synthetic peptides. The peptides which are there naturally in the organism of plant kingdom or animal kingdom, they are natural peptides. Which is man-made is synthetic peptides. Synthetic peptides finds this enormous utility. The hormones like oxytocin, vasopressin, insulin, somatostatin, etc. are the category of peptides. And you know oxytocin, it is used to induce labor pain. Insulin, it can be used as a substitute for when insulin is not produced by the body, and it has direct utility in various physiological conditions. The enzymes and enzyme inhibitors like nucleases also are peptides. The neuropeptides like neurotensin, cholecystokinin finds its use in treatment of neuropathic pain. Antibiotics, which come under the category of peptides, is gramicidin, which is having antimicrobial property, especially for bacillus species. The spider toxins, snake toxins, conotoxins acts as ion channel blockers and helps to block the neuropathic pain. These synthetic peptides which we are going to prepare can be used for diagnostic purpose and also has therapeutic agents carrying capacity. It delivers the therapeutic agent to the site of action. Peptides, structure which are structurally similar to cyclopeptide, can mimic them and produce the effect what they produce naturally. Thus, it can be used for therapeutic benefits. Transporter peptides like penetratin, oligoarginine, HIV TAT proteins, which transports certain chemical substances and helps in the process of various physiological condition. Immune peptides of which are also called as synthetic antigens. These have been used as diagnostic tools and hence it is utility is enormous. But however, peptides has its own limitation. It cannot be given through oral route as it gets digested. Hence, we have to go for alternate routes of administration. But still, peptides are one of the therapeutic agents which has been utilized to the maximum extent possible. Thus, we need to synthesize peptides. Today's subject of discussion is Peptide synthesis strategies for the same. What is peptide? Peptides are those compounds which have peptide bonds. What is this peptide bond? It is an amide linkage between two amino acids. This amide linkage connects two amino acid through this amide bond. If I take this compound as an example, I have phenylalanine linked with valine through amide linkage. This is the amide linkage which I have represented in blue coloration. And L-phenylalanine amino acid has condensed with valine, another amino acid, through the peptide bond or the amide bond. That's why it is called as N-phenylalanyl L-valine. All the amino acids which occur naturally are L isomers. This is nature's selection. All these monosaccharides, what we see, are D isomers. Here, the leucine is combined with alanine through amide bond. That's what is L-leucyl L-alanine. That's if I take the two amino acids and react, I'll get the amide linkage. The NH2 of one amino acid reacts with the carboxylic group of another amino acid, it can form a peptide bond. If I take CH3, CHNH2, COOH, alanine, precisely it is L-alanine, and react with leucine. This is isobutyl group attached to the amino acid L-leucine. This has the lone pair of electrons, nitrogen. The carbonyl carbon is the positive center. It can attack on the carbonyl carbon, OH gets kicked off, and OH minus and H plus loses its water molecule, and it can give rise to corresponding, the alanine has reacted with leucine. Or leucine, amino group of leucine has reacted with carboxy group of alanine. That's it is L-alanyl, L-leucine. To aid this reaction, we use a dehydrating agent, or it is also called as coupling agent, as it couples the two molecules of amino acids. The amino group of alanine attacks on the carbonyl group of leucine, dehydration takes place, and it can give rise to L-leucyl L-alanine. Here, two products can be formed. Or L-alanine NH2 can react with L-alanine carboxylic acid, another molecule, to give allyl alanine. Similarly, leucine can react with another leucine. Amino group of one leucine reacts with carboxylic group of another leucine to give leucyl leucine. With one reaction, we get four different products. But I want only L-leucyl L-alanine. Others I don't want. Then how to achieve that? Okay, It is a single shot reaction. We get four products. But what is not required if we get, it's of no use for us. That's why we need to have the strategy to get only one type of alanine of our requirement, the desired peptide. That's why the synthetic strategy followed for the synthesis of getting this desired peptide is like this. As this reaction use coupling reagent, it couples the molecule. That's why it is called as coupling reaction. And formation of this amide or the peptide bond between the two amino acid is a very crucial step. First, amino group, we take first amino acid, the protect the amino group and activate the carboxylic group. I take an amino acid, we treat with a protecting reagent, and the protecting reagent adds the protecting group and protects the amino group so that this amino group do not react. And I should make it the carboxylic group reactive. That's why I should activate, because OH is not a easy living group. I activate this carboxylic group by using activating reagent. And this carboxy group having activated, which is activated, and amino group protected, I have prepared. This which I have prepared, protected and activated amino acid, to be precise, amino protected carboxy activated amino acid, and then second amino acid we take and we protect the carboxy group, and then couple this protected carboxy protected amino acid with the amino protected carboxy activated amino acid to create the peptide bond. I have taken amino protected carboxy activated amino acid and treat it with the carboxy protected amino acid. Here the carboxy group of this amino acid is activated. The amino group is free in this amino acid and the carboxy group is protected. That's why I am blocking the reactivity of carboxylic acid of this amino acid, second amino acid, and activating the carboxy group of the first amino acid and blocking the amino group of the first amino acid. Now, reaction can occur. The NH2 lone pair of electrons attack on the carbonyl carbon and the peptide bond can be formed and the desired amino acid can be obtained. Then I will deprotect this amino group. I got the peptide and I react with another carboxy protected amino acid and I go on synthesize this molecule. This is the strategy which we follow to obtain the desired peptide, where we protect the amino group of the one amino acid and the carboxy group of the another amino acid, and the amino protected amino acid, I activate the carboxy group and make them to react to get the desired peptide. Two methods are utilized. One is the solution phase synthesis. In solution phase synthesis, which is the general method of synthesis which we follow in the laboratory, where we add the substrate and the reactant in a solvent and heat it. Here we are optimizing the reaction conditions to get the desired yield. And peptides or maybe tripeptides to decapeptides to number of amino acids are there added to this. And each and at every amino acid when we add, we have to purify it. First we have to isolate it and you have to purify it at each and every step. I want to prepare octopeptide. I add seven amino acids to the basic amino acid. Seven times I have to isolate and purify it. Yes, way it is time consuming. As it is time consuming, we cannot prepare the longer peptides. Smaller peptides like tetrapeptides or tripeptides or pentapeptides can be prepared by using solution phase synthesis. And as there are number of small peptides has lesser number of steps, that's why lesser number of steps of purification and hence suitable for large scale manufacturing. Solid phase peptide synthesis, in this we anchor or attach the peptide chain to the solid support which is made up of a resin, a polymer. When I attach this peptide to the solid support, that will not dissolve in the solvent which we use. That's why just by filtration, when I add the peptide, that peptide is added to the peptide chain which is already attached to a solid support. And this is in the solid phase. That's why we can filter it off and the excess reagent and this can be removed and it can be trace amount of the reagents which is attached to it can be washed away by washing procedure. And again I can add the peptide, another peptide and continue the process. And each and every step there is no need of isolation and purification, and hence it reduces the consumption of time, making it rapid, simple, and it can be repeated number of times more easily. Hence it has a very good advantage of avoiding this purification and isolation step. Thus, it is useful as it gives a better yield and there is possibility of automation. Hence, it can be used for the synthesis of longer peptides. Two methods are used. First method which was used was solution phase synthesis. Later on, solid phase peptide synthesis has been developed and this has been utilized more as and today because it has its own advantages. Thus, solid phase peptide synthesis is the order of the day. We have to protect the amino group and the amino of the amino acid and also the carboxy group of the amino acid. What are the protecting groups which we use for amines? We generally protect as carbamates. The protecting groups which we use, it should be directly and easily protect the amino group and it should be stable during the reaction and it should be easily removable, cleavable after the completion of the reaction. These are the base and it should be easy to work up and also it should be economical. These are the characteristic nature which we look into for selecting the protecting groups. The protecting groups which we use for protecting the amino and the reagents which we use for the same purpose and how we can cleave the agents which we can use for cleaving and the reaction I am summarizing here. I can protect the amino group by tertiary butyloxy carbonyl group. I use tertiary butyloxy carbonic anhydride in the presence of a base in water at 25 degrees centigrade or if at all my amino acid is water soluble. many of the times it may not be possible. Then we use methanol or DMF as solvent using the same anhydride in the presence of a organic base instead of an inorganic base. Or I can use tertiary butyloxy carbonyl azide and DMSO as the solvent for the purpose, which can donate the tertiary butyloxy carbonyl group to the amino group. It should be easily clearable. We use 3 molar HCl in the presence of a suitable solvent, or I use trifluoroacetic acid in place of HCl and thiophenol and a suitable solvent, or steric ammonium nitrate with acetonitrile. Amine I treat with tertiary butyl oxycarbonic anhydride in the presence of a base like sodium bicarbonate, either in water or tetrahydrofuran. The amino group has lone pair of electrons attack on the carbonyl group and removes this, and I'll get corresponding tertiary butyloxy carbonyl protected amino. I treat with HCl in a suitable solvent. It dissociates to give the free amine. I can also protect by using benzyl carbamate. I use benzyl oxycarbonyl chloride or benzyl oxycarbonic anhydride in the suitable solvent, and I can cleave this by using hydrogen and palladium, or hydrogen palladium in the base, or palladium with ammonium acetate, or by potassium hydroxide and methanol, or tribromoboron with DCM. I take the amino acid in which carboxy group is activated and treat with benzyl oxycarbonyl chloride in the presence of a suitable base. This has lone pair of electrons, attacks on the carbonyl carbon. Chlorine is an easy linked group. It loses HCl, which is neutralized by the base added to give the corresponding amide linkage. And thus, amino group is protected by the reaction. We can also protect by 9-fluorenyl methoxycarbonyl group. We use 9-fluorenyl methoxycarbonyl chloride in the presence of a base in a suitable solvent, or the fluorinated derivative of FMOC. We can cleave it by under acidic condition, like that of the butyloxycarbonyl protected amino. I have the amino acid in which amino group is there. I treat with 9-fluorenyl methoxycarbonyl chloride. This is the fluorenyl group. This is the methyloxy group attached to the amino group of the amino acid through the carbonyl. I'll get FMOC protection. Another protection we use is TROC. It is protected by using the 2,2,2 trichloroethyl carbamate, which can be achieved by treating 2,2,2 trichloroethyloxy carbonyl chloride in the presence of a base, and which can be cleaved by using zinc or zinc lead couple, or by tetra using ammonium acetate. Trichloroethyloxy carbonyl chloride reacts with free amino group, attacks on the carbonyl carbon, chlorine gets kicked off, the base neutralize the HCl formed, and I'll get truck protected amino. The carboxy group can also be protected in the form of esters. The protecting group, reagents and cleaving agents used, we can protect as methyl ester. We can treat with methanol, RCOH plus methanol in the presence, simple esterification reaction in the presence of HCl or H2SO4. We can cleave by using the base like lithium hydroxide or by enzymatic hydrolysis or NH2COH. I treat with methanol either in the presence of trimethyl chloride or HCl or H2SO4 to give the corresponding methyl ester. Similarly, the ethyl ester can be prepared by treating with ethanol in the presence of an acid, which can also be cleaved in the similar manner of methyl ester by using the similar reagents. We have seen we treat with ethanol, I'll get corresponding ethyl ester. Tertiary butyl esters can be used for protecting the carboxylic group, but it can be achieved by treating with tertiary butanol. This is cleaved under acidic condition, different to that of the methyl and ethyl esters, where they are cleaved by using basic conditions. I take tertiary butanol in the presence of trimethyl chloride or an acid. It attacks this undergo esterification reaction to give the corresponding tertiary butyloxy ester. Benzyl esters can be prepared by treating with benzyl alcohol, which can be cleaved under acidic conditions similar to that of tertiary butyl esters. I take butanol and the amino acid in the presence of an acid like paratoluene sulfonic acid and reflex it, and I use the azeotropic solvent with cyclohexane, which removes the water which is formed and makes the reaction to move forward to give rise to corresponding benzyl ester. This is how we can protect the carboxy group and the amino group and make them to react by activating the carboxylic group of one of the amino acid. How we activate the carboxylic acid? What are the activating reagents which we can use? And what are the varieties of reagents available? All this will be the subject of discussion for the coming class of presentation. Till then, have a nice day. Thank you for your hearing.